So we have seen how to do it for the sphere, for solid as well as hollow. And we have seen for the point charge. So now we can go for the line charge. So E due to infinitely long line charge. So if you have infinitely long line charge, it means it will follow which kind of symmetry, guys? Tell me.
Cylindrical.
Very good. So you know that it will have cylindrical symmetry. So you know what kind of Gaussian surface we must plot or draw here. So assuming the lambda is the linear charge density, the Gaussian surface you are going to plot will be a cylinder. And definitely the cylinder must be closed cylinder, right? So let's move this drawing. So let's say if you want to know the electric field at a distance r from the charge wire, you can say, then we must draw a cylinder of radius r, correct?
Yeah.
And you know the process. What to write next part? The LHS is what?
E 2 pi r.
So we have this Gauss law, and the length will have to take L. The radius is r. So the flux will be from which surface? The flat or the curved or the both? We have discussed this yesterday.
Of surface.
So
Curved
E dot
surface.
dA, yeah, very good. So E dot dA we must write equals to how much? What we should write here?
It will be
Yeah, it will be
2 pi r.
E 2 pi r l.
very good. It is E 2 pi R. And then the question is, what is the charge enclosed by
Lambda
this?
l.
Very good. Upon epsilon naught.
Epsilon naught.
So now you can see the L will cancel out, and we have a E as a definition, which is very nice to remember. Lambda upon 2 pi epsilon naught into R into sorry, L will cancel out into R, which you can also write as 2 lambda by 4 pi epsilon naught R. And we know 1 by 4 pi epsilon naught is called K. So this is 2K lambda by R. So we have derived this already using the rod formula, where alpha beta tending to pi by 2 gave the same answer. And now the Gauss law is giving answer in a very simple manner, isn't it? So that's so
Yes.
powerful, very, very powerful. So once you derive this formula, the next question you can solve is E due to Okay, so electric field due to infinitely large hollow cylinder with uniform surface charge density sigma. Let me draw it first, how it will look like. Okay, so this is infinitely long cylinder, and sigma is the surface charge density. So you may have another representation called the cross-sectional view representation, which is very famous. So this is your question. You have to find the electric field inside as well as outside. So find E when R is less than R and R is more than equals to capital R. Capital R is what? It's the radius of the outer circle where the charge is residing. Something that basically the charge is here, so it's fine. All right, guys. So you can tell me the answer. Not very difficult. So what will be the answer for inside? Name audible? Hello, hello, 1, 2, 3.
Yes.
Audible.
So what is the value for the E inside the hollow cylindrical shell? So this is a cylindrical shell. So and it is uniformly charged. So inside the shell, the electric field will be how much? I think my question
Will
is
it
not
be
hard.
0?
Yeah, it will be zero, no, because
Yes.
there is no charge enclosed, right? If you draw
Yes.
any Gaussian surface. Okay. So we'll also prove it by other method. There is other way of doing it.
Answer for the inside, it will be sigma R by R.
Inside or
epsilon.
outside? Outside.
Outside. So,
Yeah.
sigma R by R epsilon.
Sigma R by R epsilon. Okay. You are going to say sigma r by
Bigger.
like this, huh?
Yes.
Yeah, seems to be correct. Okay. So anybody else getting the answer? I think this is the right answer. So if you want to find the electric field at any point r outside, you must draw the Gaussian surface of radius r. Correct?
Yes.
And the Gaussian surface can have any height, it doesn't matter. What really matters is the radius of the surface, cylindrical surface must be r. So once you draw a Gaussian surface, we all know that flux through the flat is zero. So these surfaces will have no contribution to flux, as we have discussed in the last lecture. I need not to explain again. So the LHS is going to be fixed, right? What we are going to have the LHS here?
E 2 pi r.
LHS E. You're making again the same mistake. Eh? E 2 pi r
Into height, its height.
into
I
height.
told the same thing.
Okay, I think L was silent. Maybe.
Maybe.
So E into 2 pi r L. And the RHS will be how much? How
Sigma
much?
into the area.
So the area is how much? How much we should write here?
Or 2 pi r. Like bigger.
Very good. Upon epsilon naught, right?
Yes.
So you can get the answer sigma r by epsilon naught r, which is the right answer. And essentially, we can also define lambda for the cylindrical surface. So what is the lambda equivalent of the cylinder in terms of sigma? It's a very interesting lambda and sigma relation. For a cylinder, we can always write.
Lambda is sigma d.
So lambda is how much?
Sigma into L.
Okay, you can take a length L of the cylinder. The charge on the cylinder will be lambda into L.
Yes.
Now the same charge we can also express in terms of sigma. How to express? How much charge L length of cylinder will contain?
2 pi r.
2 pi r.
Sigma into 2 pi r L. I think you need to learn to spell L actually. You're making it silent. Okay. So the L will cancel out, right?
Yes.
Yeah.
What you need to realize that lambda and sigma are two separate representation of charge. And in reality, I have explained before also, in reality, except volume charge density, everything else is a representational way of writing, which means it is a matter of convenience to write in terms of sigma or in terms of lambda. Now imagine if I want to write in terms of rho, and if I imagine if the thickness of the shell is of some importance, let's say this is T, and the charge is filled in this entire thickness. At the same time, how to express this in terms of rho? We can write a volume equals to, so for a thin shell where thickness is very, very small compared to the radius, how we write volume? So we write the perimeter into thickness. So do you know different way of writing? Lambda into L or sigma into 2 pi RL or rho into 2 pi RL into T, all are same thing. Do you guys realize this? So are you guys understand the last part, the row part, how to express the same
Yes,
thing in
Yes.
terms of volume charge density? So let's say if you are interested in relating lambda with rho, you can see the lambda with rho will be how much? Lambda equals to 2 pi RT. The L will be not there, right? If you want to relate sigma and rho, how to look like? Sigma equals to rho T. The volume charge density into thickness of the shell will give you the sigma. Understood? So these all are representational. And what is the benefit of knowing all this interconnection of the various representational technique? So the moment you go outside the center, the lines of force will move readily away. Anybody observing it, you can think this is the light ray coming out of the cylinder. And if you trace back those light rays, like I'm taking that as the equivalent of field lines, if you trace those electric field lines backward, where they will meet? Every lines of force, if you trace back, where they will eventually converge?
Center.
At the axis. At the axis of center, all field lines will converge, right? So now it is as good as a line charge, and therefore formula will remain same as the line charge formula. So what was the formula for line charge? If you remember, lambda by epsilon naught r.
yes,
Okay. And now we have, I mean, we know the relation of lambda with the cylindrical surface. So it is sigma into 2 pi r, correct? The lambda and sigma relation. So sigma into perimeter is lambda. And you can see without remembering or deriving, you can get the answer directly. Only by using the conversion. Okay. So I will tell you what is lambda. Lambda is sigma into perimeter. For cylinder. And lambda is rho into cross-sectional area. That's a thumb rule. Okay, and sigma equals to rho into thickness. Understood? So whenever sigma is mentioned, it means it is mentioned over a surface which will have some thickness, and therefore the rho will rho and sigma we can always relate with these relations, and you must remember these all. Don't remember, try to derive it by equivalenting the charge, like by equating the charge, consider a part of it, try to calculate the charge in different representational technique, and I mean just equate it, you will get simple relations like this. Is this clear, guys? Maybe.
yes,
Yeah.
What is the lambda? Yeah, so we got the lambda relation of rho. This is very interesting. So this will help you. Okay, now the question was like I was talking about. Of course, we prove using Gauss law that the field must be zero, but can we prove it otherwise? The answer is yes, we can prove it otherwise. And the proof goes like this. You can see this is the cross-sectional view, right? And if I choose any point P, I want to prove that no matter which point you choose P, the field is 0 here. So to prove that, I will draw a line passing through P, just like that. And I'll draw one small angle. And then you can see something interesting here. Let's see, I hope you're seeing something interesting. So I have cut a small piece of cylinder, right? So I have this two small piece of cylinder. And what this piece represent, the white dot represents. Can you tell me what is this representing? Any idea? Maybe, may not.
Area.
No, it is representing an infinite line charge. Do you realize, guys? This is infinite line charge.
Yeah.
The white one.
The white one. The white one is the cross-sectional view. So in the cross-sectional view, what you're looking right now is the infinite line charge, two infinite line charge. Do you realize this? Maybe. Or may not.
Yes.
Anybody who is able to understand this is two infinite line charge?
Yeah.
So if I call this angle as d theta, this is also d theta, right? And if we have a center like here, so this angle, if I call alpha, this is also alpha, right? Now why alpha? I think. So now, what is the length? This length. What is this length? Can you guess? So this length is roughly r2 d theta, some value cos or sin alpha. So basically, this length will be, if this is r2, this is d theta. So this length will be r2 d theta, right? And if I call this as dl or r2 d theta, so it will have some component. So what is the formula for? Okay, anyway. So what I'm trying to explain, how to write a lambda with relation with sigma, right? So lambda is defined as sigma into perimeter, and here perimeter means the width. So more the width you will take, more the lambda it will have, because we will be covering more charge for sure, right? So this part will have, let's say, lambda 1, and this part, let's say, it will have lambda. I'll prove it. What is this? So now let's try to find the field at P. So field at P, can we write like D1 minus D2 modulus? I don't know which one is bigger. Can we write like this?
Yes.
Now the first will create a field by the formula lambda 1 by 2 pi epsilon naught R1. And second will create the formula as lambda 2 by 2 pi epsilon naught R2. Why? Because these are infinite line charge. Do you realize this? Maybe. Okay. And the lambda we can write as sigma into the length, which is R1 d theta, into sin of cos alpha. I mean, let me see this. This will be cos alpha. So this will be R1 d theta cos alpha and 2 pi epsilon naught R1. And then lambda 2 becomes lambda sigma into R2 d theta cos alpha upon the same formula. And you can see something interesting. No matter which point you choose, the R1 will get cancelled. R2 gets cancelled. So what we are left with? The DEP will be how much? You can see clearly. Because R1 gets cancelled, everything is same on both sides, right? So electric field will be zero inside the uniformly charged cylinder. Can we say that for non-uniform cylinder it will be also zero? Can we say? Can we say that if the cylinder is non-uniform, still the inside will be zero?
Yes, sir.
Can we say?
Yeah, it will be 0.
For what? Inform or non-inform?
Both.
Both.
Yeah.
But if it is non-uniform, then sigma will not be same no? At these two locations. So what if the sigma at these two locations changes? Will it cancel out? Tell me, guys. If we consider sigma differently at these two locations, can we say this will cancel out? For sure.
Yes.
No, sir.
See, here it is getting cancelled because sigma is same, isn't it? We are able to represent lambda 1, lambda 2 in terms of sigma only. So what if the sigma is variable over the surface? Then this will not be the mandatory condition that sigma 1 is cancelling the sigma. And therefore, the moment it is non-uniform distribution, there will be field inside as well. Am I clear, guys? What I'm saying?
Yes, sir.
So what we must remember that this relation, the application of Gauss law is only meant for uniform surface charge density. For non-uniform, it is non-zero. Actually, it's non-zero. And the same is also true for the hollow shell, spherical shell. So if you have a hollow spherical shell, I mean, of course, spherical shell is hollow. If you have the spherical shell with uniform charge density, then inside is zero. So what if it is non-uniform? Can we say it is also zero again? We cannot say. No, it won't be zero for sure. So always remember that only for uniform distribution in hollow object you consider the inner field to be zero. You cannot do the same the moment it goes non-uniform distribution of charge. So I hope I'm clear what I'm saying. So shall we put this into word or is it okay if you remember? Let me put into words. So I'll put it here. So what we can write for uniform charge distribution over spherical or cylindrical or infinitely long cylindrical, okay, let me over spherical shell or infinitely long cylindrical shell E inside electric field inside will be zero for non-uniform distribution. It won't be zero. So for non-uniform distribution, it won't be zero. We have to be very careful. We cannot say it is zero. So just because something is infinite will not make sure that the answer is zero. So Gauss law is not the right way to get the answer, because Gauss law is only saying that E dot dA equals to Q enclosed by epsilon naught. But you have no idea that E dot dA is well defined or not. So for non-uniform distribution, the E dot dA is not well defined itself. You have no idea how it will look like, how the E will be. And therefore, if you just apply mentally the Gauss law and you will say that E dot dA is Q enclosed by epsilon naught, and just because the Q enclosed is zero, you cannot end up saying that the field must be zero. Okay. So those things are very, very important and you have to be careful about it. Let's go to the third part. So E due to infinitely long. Solid cylinder. Now I would like to say something. The word solid is inherently understood. It means we never need to mention the word solid. Only the hollow is mentioned. So when I say cylinder, you must assume solid cylinder. When I say sphere, you must understand solid sphere. If I need to mention hollow, I'll mention it explicitly. So while solving numerical, make sure that the word is perfectly interpreted. So by default, sphere, cylinder, or cube, when we say without the word hollow or shell, it means these are solid only, and therefore there should not be any ambiguity in your mind. Okay. So due to infinitely long cylinder with volume, charge density, rho, and the radius capital R. Okay. Let me try to draw it. So the cylinder is never ending, and the radius of the cylinder is capital R. So the obvious question is, we will ask the electric field at any distance R from the cylinder's axis, and the R may be inside and R may be outside. So guys, please do this favor. Tell me the answer when R is less than R, and then answer when R is more than equals to R. So there will be two answers, and find the answer and do plot the graph. Okay, in the last lecture, last topic also, we should have plotted the graph. Nevertheless, I'll plot the graph both here. I have a space here, Okay. So are you guys solving the question? The solid cylinder? Solid cylinder,
Then I
please do it.
got the answer.
You got the answer also?
Yes, for the first one. It
Okay.
is a rho r by 2 epsilon.
Excellent. And for the other?
I'm getting rho r square, like big R square upon 2 epsilon naught r.
I think that's correct only. Very good. So anybody else getting the answer? Come on, guys, tell me the answer first. So here you can also write it for E inside. In vector form, you can see it will be radially away. The direction of R vector will be the direction of E inside. And for outside, it will act as a line charge again. So you can write directly also. Let me give you the answer again. It's a lambda by. I can apply a lambda for both cases to get the same answer. So with only one formula, I can get all of the answers. So how? So let's say if you want to find the inside. Inside means up to R radius. So rho into pi r square is the lambda. And this is the answer, right? And for outside, we can write like that's same answer. Inside, using only lambda variation, you can get all answer. The moment you go outside, the lambda will be restricted to capital R, but the moment you are inside, the lambda will be restricted to the area of cross section that you have covered so far, not the entire area. And the area which you have covered so far is pi r square if you are inside, right? Is this making some sense to you guys? Yes or no?
Yes.
Yes.
So how many of you got the answer? Raise your hand. Only one hand. Okay. Those who have got the answer, raise your hand. Okay. 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 Fine. All right. So those who have not derived, let me draw this. E inside into 2 pi RL. The same strategy is the Q enclosed is pi r square h upon epsilon naught. You can do this way, you will get the answer. And for E outside into 2 pi RL, the charge enclosed will be only up to the capital R radius. I hope you are getting the idea why these are the answers. And now let me plot the graph. So for the hollow shell, the field will be only outside, right?
Yes.
And it is 1 by R proportional relation. And for the solid cylinder, first it will grow linearly up to the surface, and then it will decay by 1 by R, right?
Yes.
Yes.
So everything is important. You need to understand the graph is very integral part of JEE syllabus. So the moment you learn physics, you must learn the graph. So at the surface, the answer will be how much? Rho r by 2 option of, right? At surface. Okay. So now we can do the similar variation as we did for uh, the sphere. But the problem is here you need to know how to take element in case of cylinder. So solve the previous question.
Sir, I think you have hinted that when you taught us lambda and that. Like the thickness and the
Correct.
length.
So solve the previous question when rho is a variable. So find the electric field inside as well as outside as a function of R. So the rho is varying only away from the axis. As you move away from axis, the rho will vary. But if you move parallel to the axis, it will remain same. Understood? That's the meaning of this rho value. So try this out and tell me the answer. What is E inside? Everyone, please go ahead. Everyone, please do try this question and tell me where you are getting stuck. Are you able to understand how to take elementary? Yes or no?
Hello.
Yeah, tell me.
Is it rho naught bracket r by 2 minus r square upon 3r upon epsilon?
I think this is correct answer. R by 2 minus R square by 3R is correct. So, and what is E outside?
So the smaller will be replaced by bigger.
No, no.
Uh,
The moment you go outside, the charge enclosed will get constant, right? So
okay, yes.
the lambda will be saturated. So you have to find the lambda accordingly.
Okay.
Or you can do the integration of charge enclosed for the L length cylinder. It is
Yes.
infinite, but you can choose L length and you can find the charge. That's easy. So in physics, we have very much limited processes. Once you learn one, process at one place, you can apply everywhere else. So let's say you are doing for electrostatics, you know how to do the integration, how to take elementary, how to relate lambda, sigma, rho, and all. Then similar idea will also help you in deriving the formula for gravitation. In fact, we are going to do it right away. Only symbol changes, but not the process. The method to take elementary remains same throughout physics, whether you are finding the moment of inertia or you are doing the question of electrostatics or gravitation or EMI or matrices. There is a foolproof pattern throughout. And try to learn the basics, like what is the method to derive something, what kind of elementary we cut to get the answer. And once you realize this part, almost 50% physics you have covered without solving any question. Then what really matters is knowing the formula and getting the answer using derivation. This is done, guys. So let's say, if you're deriving, you can write E out into 2 pi RL, and the Q enclosed we can write as rho dV. upon epsilon naught, right?
Yes.
And the rho we can write as rho naught 1 minus I r by r. And what is dv here? 2
2
pi
pi
r
r
l
dr.
dr.
Yes, correct.
That's
Sir, I got the
if we
out
know.
answer also.
Yeah.
A rho naught r square upon 6 r.
This will go from r to capital R, right?
Yes, correct.
Because beyond r, the integration will be giving you zero answer, right? Because there is nothing present outside, right? So even though you will integrate from 0 to r, you can break into two parts. R to r, rho dv. But do we have rho outside this r? Do we have rho outside
No.
this r? No. So this is actually 0. That's why
0.
anyway this term will not come. Okay. So your answer would be E out 2 pi RLHS, and the RHS is 2 pi rho naught L will be outside. That we have R minus R square by sorry, dr. And what we are left with, you can see clearly. So it is R square by 2 minus R cube by 3R, which is like R square by 6, right? Am I right?
Yes, same.
So the E outside turns out to be I hope this is the answer.
Yes, I got the same.
Very good. So how many of you are able to do the integration part without getting worried, like you know how to do the integration? Don't say that you don't know integration, it is not taught in school and so on, because this is the most basic integration. It doesn't need
Yes, so it is easy.
any extra information. It's a very basic one. And see, if you're not getting the integration right, then my only suggestion is you go home today, no matter what, just do the integration. I mean, take elementary, do the integration, maybe 10 times, 20 times, or 100 times, till you get it right. Because this skill is something that everyone needs to develop. If you're not able to develop, you will never sail through the physics. That's for sure. And now again, because E is a function, you can see it's a quadratic. So can we say we can find the condition for E max?
Yes.
So for E max, the dE by dr must be 0. And this will imply 1 by 2 minus 2r by 3r equals to 0. So r turns out to be
3
3r
by
by
4.
4. So in case of sphere, it was 2r by 3. Now it is 3r by 4. In case of cylinder. And the value of E max we can also find by resubstituting the r value. R by 2, which is 3r by 8. And 1 by 3r into r square, which is 3r whole square by 60. It is 3r by 16. Correct? This is the answer. And again, we cannot end our discussion without the graph. And you can see the graph we have drawn before also, it is something similar, right? So a quadratic plot which meets the hyperbolic graph into the regions quadratic and this is, oh, now we can say hyperbolic. And the maxima will be before the R. I hope this is clear. Graph part is clear. I think everything is clear. If you
Yes.
have doubt, please do ask. I'll proceed to the next concept. So how to deal with the variable constant concept is clear.
Yes.
Yes.
Yeah.
So we have done the cylinder, we have done the sphere. We can go back to something called uh, the sheet. Okay, I'll finish the traditional one, then I'll go for the unconventional one. E due to infinitely large okay, now I'll say something interesting. So E due to infinitely charged non-conducting sheet with uniform charge distribution sigma. Now let me underline this part first. The word non-conducting is not necessary to be mentioned. The reason is when I say anything, it is by default non-conducting medium. So the moment I say a charge is put over a sheet, it is non-conducting. A charge is put over a sphere, it is non-conducting. Cylinder, non-conducting. So the by default is non-conducting. Conducting is something in unique, something uh, special. So it should be mentioned explicitly. So until I am not using the word conducting, by default assumption remains non-conducting. Always remember this idea. This is something by default assumption. Just like when without saying it goes solid. Similarly, without saying it goes non-conducting. So if the charge is spread over a volume, which is not the nature of conductor, conductor will throw it out. Only the non-conductor can keep it inside, and therefore conductors will behave differently than the non-conductors. So if I am mentioning the word conductor, then take it. If I'm not mentioning, don't take it. So by default, what we will take? The medium as
Non-conducting.
Non-conducting.
non-conducting. Without, I mean, without saying it goes like this, non-conducting. And before I will teach you conductor, I mean, I'll teach you the entire property of conductor. I think I have missed the discussion of electric lines of force due to conductor, right? Two or three things I have just left separately, so I'll take it now after this question. So E due to infinitely large non-conducting sheet with uniform charge distribution sigma, and we know how to do it. So it is definitely infinitely large from all dimensions. So every sheet will have by default some thickness. Okay. Now thickness is generally not talked about always, but only in context when it is required. So let's say the reality is the charge is here is volume charge density. But because thickness is so small compared to the area, we end up seeing this as surface. The whole idea of surface is controversial. We don't have something like surface. We always have volume. So when I say charge surface in any scenario, some thickness is always assumed and it goes without saying. So if I consider a small patch, it is like a button. And the button will have thickness T. And let's say the area is dA. So how much charge this button will have? Rho dA into T, volume into density. But the sigma, as I said, sigma is the representational way. So when you choose sigma, you will try to write the answer in terms of visible area, the area which you see, the area which you're considering over the surface. So we write sigma dA is my way of writing the same charge. So charge in this volume, can be written in these two forms. Either rho dA into thickness or sigma into dA. And as I said, sigma, lambda are representational value. The reality always remains rho. So therefore, we can clearly say the sigma into T, rho into T is sigma, as we have discussed earlier also. So you need to understand what exactly you mean by sigma. The volume charge density into the entire thickness over which the charge resides. That thickness, when you multiply with rho, you get the sigma equivalent of the sheet. I hope this is clear. And now the question is how to take the Gaussian surface. We have discussed how to draw Gaussian surface. So what we'll do is we'll draw the cross-sectional view only, the side view, the thickness part, and then you can draw a cylinder, which is penetrating both ends. So now the electric field that the sheet will create will have the direction like this on the right and left. Okay, I'll do that. So what is the total flux here? The E dot dA becomes how much? You can see clearly. So for this area, for any closed surface, the area vector of the right flat part will be towards right only. And for the left flat part, it will be left, right? So can we write that total flux as EA plus EA?
Yeah.
Yes.
But the charge enclosed is only this much, which is how much? In terms of sigma, it is how much? So in terms of sigma, how much is this? Come on, guys, what is the charge here inside the box? What is the charge? How to write this charge enclosed in terms of sigma?
Sigma into the area. Yes. Upon epsilon.
So the net electric field turns out to be how much?
Sigma upon.
Is this clear?
Yes, sir.
So for non-conducting sheet, the way sigma is defined, the answer turns out to be sigma upon 2 epsilon naught. Okay.
Yes.
So now comes the last derivation, which is the conducting sheet. But I think we haven't discussed about the concept of electric field lines for conductors, right? Have we discussed before? No.
No.
So what I'll do is I'll give you the brief, not brief, the complete theory of conductors, and then we'll go back to the problem. Okay. So today's discussion is going to be all about conductors. So what makes the country? What makes the country?
People.
What makes the country?
People.
It's people, right?
Yeah.
Conductor is no more different. It is a medium again. But what makes a medium conductor? How it is different from the rest of the medium? And in what manner it is different? That is what we need to investigate. So this is a medium, even the conductor falls into the same category, but because of some unique property or characteristic, we call it by different name and we call it conductors. So when I say non-conductor, again it's a medium. When I say conductor, it's a medium. So medium means anything which occupies some matter. We can call medium. So the air is a medium. Why? Because air contains air molecules, of course. Then vacuum is the lack of matter. When we have nothing, no matter, we call it vacuum. Then vacuum is not empty. So even nothing is there in vacuum, what we have there? We call it energy. So there is nothing like complete emptiness. Emptiness is again kind of a relative idea. So if you say the vacuum is empty, it's wrong. Vacuum is filled with energy. So we can have a vacuum with no energy, then we call it dark matter. And most part of the universe is filled with dark matter. And then we have energy. And when matter will meet the dark matter, again it will annihilate each other and will form the energy. Okay, anyway, this is plus. So theory of conductors says that a conductor is identified by its ability to conduct free charge, or you can say conduct electrons. So it will have a large reservoir of free charge carrier which can be moved under the influence of external electric field. Now, in case of insulator, the charges are bound charges. They cannot move freely. So it is like every person living in the medium called non-conductor. Every charge is attached to some sort of spring. So you may move locally here and there, but you will always remain confined to your localized destination. So the bulk movement won't be possible. You cannot move from one place to other place freely. Unlike conductors, where it is feasible, they can move. If required, they can move. So conductor is identified by a medium with free charge carrier. And the free charge carrier concept is not like feasible for every medium. That's why we have classification as conductors and non-conductors. Okay. So it's a very developed civilization where the liberty is too much given to its citizen. You can move freely, and they have the Euro passport, so they can move to any European country. All countries connected. So the ability to conduct electron gives you some extra power. So we'll try to explore what is that extra power that you get owing to the free charge carrier. So let me just put into words what is conductor. So we can add conductor is a medium with inexhaustible supply of free charge carrier. Okay, electron is charge carrier. Electron is not charge itself. Electron is a matter which carries charge and mass both. So conductor is a medium with inexhaustible supply of free charge carrier. It means for any practical purpose, whatever number of electron you need, you can draw from conductors. So we call it inexhaustible supply. The problem with insulator is they have fixed charge. They have bound charges. So we'll talk about the bound charge idea when we start capacitor. There I will discuss it separately. Right now we just need to understand the conductor and its property or behavior. Conductors are having the crystalline structure of atoms, which means every atom will have some finite geometry. So a finite geometry, when it repeats itself over the space, we call a crystalline structure. And what is the opposite of crystalline?
Amorphous.
Amorphous, the shapelessness. So amorphous was the name of the Greek god, and the gods are shapeless or formless. Basically, amorphous means something without a form is called amorphous. So when I say morph, it's a form. Amorph, no form. So now, having this crystalline structure, the atoms are located in their finite fixed point, and these fixed point we call lattice or lattice points, to be more precise. So atoms will occupy all the lattice points which are finite geometrical location, and then they will have some voids, some empty space. And these voids are not very large, of course. The voids are very small, but the size of electron is so small that even the voids available between the atom inside the crystal or crystalline substance or a conductor is large enough for them to roam. So you can imagine the size of electron, how small the electron is. It can roam freely. It is like you are in the basement parking and a car is everywhere. Every stack is completely filled. But still the space is good enough for the dogs to run, for the rat to do all the must in the car parking, isn't it? Of course, you won't be able to park your car because there is no space left. But still, the empty space is good enough for the mosquitoes to have a happy life forever. So that's a dimensional comparison you can do with the empty space and the electron. Electron is like the mosquito in the car parking. Even the car parking is completely filled, the mosquito will have no issue in flying. So now these electrons which are free, the moment you apply some electric field, they start moving. Okay. So imagine a conductor. So imagine this is the conductor. Of course, you cannot see what is inside. But you have to believe that this conductor will have free electrons and the electron will be in the large number. Okay. And now let's say you bring a charge. Now the charge is unaware that conductor is kept somewhere nearby it. So for the time being, let us assume that there is no conductor. And if there is no conductor, how the field lines will be? Radially outward from the point charge? Yes or no?
Yes.
Yes.
Now I'm not drawing the field lines, I'm drawing some hypothetical assumption that what if it is there then. And definitely I'm not drawing all the field lines. I'm only drawing the field lines which can possibly pass through the volume of conductor. Okay, the other place will have also field, don't worry, but I'm not drawing it. So these field lines are representing what? Electric field, correct? So let us assume a small a hole in the conductor like this, a very tiny hole. And we'll focus our discussion to this volume, this tiny volume. So can you guys look at the electric field lines in this thin cylinder, thin pipe? Can you see the electric field? Yeah. So imagine imagine any electron in this tube. Will this electron experience force because of the field? Yes or no? So this electron in the tube will experience electric force. Tell me yes or no. Do you realize the
Yes.
electron will experience electric force?
Yes.
Yes.
And what will be its direction? What will be its direction? Towards the right or towards the left? Pardon?
Opposite to the direction of electric field.
Very good. So it will be opposite to the direction of electric field. Now the force will act. So the question is it possible for the electron to react to the force? Which means can it move along with the direction of force?
No.
The answer is yes, because it's a free electron, which gives the ability to move because of the force. Understood? So that is the property of conductor, because the conductor is having a large supply of free electrons. The moment you apply the field, the charge will start moving towards opposite to the applied direction of field. So this electron will move opposite to the field, yes or no?
Yes.
And if it will move opposite, then it will eventually where it will stop? The only place it can stop is the surface,
Yeah.
because the medium, it is the medium in which it can walk. But the moment you reach the rooftop of the building, can you move further? That's the question. So imagine the surface is the rooftop. If every person will go to the rooftop, then it requires guts to jump from the rooftop. Don't do that. It's very serious offense. So for that, we need some extra energy. That's called the some other emission. We can photoelectric emission and something else. So when the electrons is all in the rooftop, they get some energy to leave the surface, and that will be called work function, right? You might have studied in photoelectric effect. So this electron is not having that energy to leave the surface. It can go up to the surface. And that is the end of the world. I mean, it has to stop there. So this electron will eventually come to this surface and will stop. So we can say this end of the conductor will acquire some negative charge. Relatively, yes or no?
Yes.
And every space between the center will remain neutral, because when the electron will move from here, some other electron will come and occupy that place. And then the next part will again come back and this come back. There's a hopping happening everywhere. They will hop the place. So when the electron will eventually reach the left end, every other point will still remain neutral except the last place, because here the electron will hop and here it will create a deficiency. So deficiency of electron, how we represent?
Pause.
By positive charge. So positive is like a deficiency of electron and negative is like excess of electron. Do you realize this, what I'm saying? So as a whole, when this process will continue, some charge will deposit on the two ends of the tube that I have drawn. And this accumulation of charge, let me draw it separate. Imagine this is the tube which I'm drawing separately. So let's say this entire end acquires a negative charge. Sorry. So now you can see we have positive charge on the right side and the negative on the left. So this plus and this minus will induce its own electric field. So what will be the direction of induced field, guys? And the property of the induced field is it is a confined field. It is the field which remains within the body itself. Okay. Whereas the applied field is, okay, I'll just change that. Yes. The applied field is everywhere. It is inside the body as well as outside. The extension of the applied field is throughout the space. The induced field is only from the plus to the minus. Okay. And because it is equally negative and equally positive, so all the lines of force which will begin from the plus will terminate at the minus. The world of the induced field is very much confined. So after some time, now electron will be under the action of two separate fields. I'm drawing it one by one, like we are not superimposing or getting the net value. We are keeping it separate. Each field we are keeping it separate. So now the electron will experience two force. So it was experiencing the force opposite to the applied field of value Q into E. But now the induced field will also apply force like this. Yes or no? Do you realize this, guys? What is happening here? So electron was not aware that this will happen. So earlier it was experiencing force and was going towards left, but in the due process, induction happened and some field got induced within the volume of conductor. Now, as long as the applied field is stronger than the induced field, what will happen? The electron will keep on shifting towards left, and so the charge will grow in value. Yes or no?
Yeah.
Yes.
And if charge will grow in value, then E induced will also grow in value. Yes or no?
Yeah.
And if E induced will increase, so the force will also increase due to the induced field. Yes or no?
Yes.
So a time will come when both will be equal. Yes or no?
Yeah.
And it has to. So eventually, in an equilibrium situation, within the volume of conductor, the applied always balances the induced. And therefore, the net electric field inside the volume of conductor, inside the conductor, is bound to become zero, and that is the main property of conductor. That no matter what, a neutral conductor, if a conductor is neutral electrically, you are not giving any charge. If a conductor is neutral, sorry, and if such conductor is kept in external electric field, it will rearrange its free charge. It will throw the free charge over the surface. It will simply scatter its free charge in a fashion, in a manner which will make sure that the resultant field inside the conductor is zero. Once again, the moment you throw a neutral conductor into electric field, the field will create the induction process, which in turn will recreate a new type of charge distribution over the surface. That this new distribution will make sure that the resultant electric field will be zero. Now, how the conductor achieve that? That's the property of conductor. We will leave it to conductor itself. So this complex mechanism of neutralizing the net field within its volume is what makes conductor so special. Is this part clear, guys? What I'm saying? This is very deep. The moment you throw a conductor, a neutral conductor in any external electric field, it will redistribute the charge over its surface. Now, mind you, the bulk, the volume of conductor is still neutral. All the induction effect will show you the charge over the surface. And this distribution will make sure that the net field is zero within the volume of conductor. That's the whole property, whole idea we need to realize. So let me put this into word. If a conductor is kept, if a okay, if a neutral conductor is kept in an external electric field, then it will induce charge over its surface in order to make the resultant electric field inside the bulk zero at electrostatic equilibrium. So there is a delay process. It will take some time to do so. Okay. And what is that sometime? Can you guess the time? The average time it takes to do all these processes 10 to the power minus 8 seconds. So in a way, we can say it is such a instantaneous process that the moment to bring a conductor into the external field, it is done. There is no delay, it's instantaneous process. Although I have explained in next time in last 15 minutes, but what I said in 15 minutes occurs in 10 to the power minus 8 seconds because the field propagate at a speed of light. So any dimension if you take and if you divide by, because the object which we are considering is very small, so I can say the light will take few nanoseconds to cross it. So the order in which these things happens is 10 to the power minus 8 seconds, which is also the order in which the electron uh, takes to transit from the high orbit to the low orbit. So transition of electron is also of this magnitude in terms of time calculation. So you can imagine you bring a conductor into the field and it's done. Now, I have said in the very beginning that electric field lines we draw for the resultant field, not for the individual field. So this depiction is not correct. It's just to describe the situation. Okay. So whenever we draw the electric field lines, we only draw the resultant field lines. Therefore, how the field lines will appear? That's the question. So now we know that the net field is going to be zero inside, right?
Yes.
So eventually the net will be zero, which means any volume which is deprived of field, we cannot draw the field lines in that volume. So the electric field lines should not be drawn inside the volume of conductor. If you are drawing, it's wrong. So in terms of drawing, then what will be the actual field lines that one should draw? Because the previous one is not correct. Disclaimer. Picture here. So picture here is just for illustration purpose. Don't take it for academic purpose. I mean, how to say this? I hope you understood. Okay. So now the way to draw the lines force is the lines of force will begin from the plus charge, and as a result of induction, the negative will appear in the nearby surface. So the facing surface of conductor will acquire the opposite charge. So if you bring a plus, the facing must have minus, right? And the other end will get the deficiency due to the movement of electrons, it will get the positive charge. So this is somewhat like a rough charge distribution. We cannot draw it exact. I don't know how to do it. For that matter, no one knows. And what we know exactly, that the thing that we must remember as a student, you must remember this property, the net. Now, when I say net, it means not individual. So if someone will ask you the electric field due to this charge is zero inside the conductor, is it true or false? The electric field at a point P due to this charge is zero, is it true or false statement?
False.
No.
At point P, the net field is zero. Can we say it is zero due to the individual charge?
No.
No.
It is zero due to everyone, like the charge which you have brought and the charge which got induced over the surface, all together creates zero field, not independently. So the field at point P will be present due to this. That's totally true. And it is also quite possible that the charge induced may create the field here also. What really we know that the net is going to be zero. Okay. So do remember this concept. The net is zero. The individual may exist. Am I clear? And how we draw, it's very simple. The lines of force will start and will terminate on the surface. And the way it will terminate is always perpendicular. So I'll come to that why only perpendicular, why not at some angle. Okay. So the lines of force will emerge from the plus charge and will terminate perpendicular to the surface of conductor. So again, this is something which you have to be very careful. Any angle other than 90, if shown in the option while solving question in examination, if the angle is not 90, it means it is incorrect. And all the positive, all the lines force leaving the plus will terminate on the minus. And from the positive charge on the other side will again reborn and will move like this. It will again start at a right angle. So now the question is, why 90? Why not other angle? Okay. So can you guess, guys, why 90? There are many interpretations.
Otherwise they would intersect with each other.
No, that's not the logic. I mean, if I draw something like this, what's the harm if I just, because it is anyway terminating, right? Does it really matter what angle I'm showing here?
No.
You can explain in multiple ways. We have discussed this. If you go very close to any surface, it will be flat surface, right?
Yes.
And tell me, guys, for flat surface, the field will be, if you go very close, the flat surface will become infinite sheet. And we all know the infinite sheet will have the electric field normal to the surface.
Yeah.
Yes or no? Do you realize this? What we have, what I'm just saying. Every point on the surface will, every small patch which you draw over the surface will act as infinite sheet for those points which are very, very close to the surface. Am I right?
Yeah.
And for any infinite sheet, what is the direction of field?
Perpendicular to its plane.
So what I have drawn is correct? Yes or no? Because I have drawn the net field near the surface, which is perpendicular, correct?
Yeah.
That is logical, no? The net field is bound to be perpendicular near the surface. So the moment you come near, see, you can have any curvature, but the moment you reach the surface, you are going to hit at right angle. So negative will terminate and positive will emanate, but both event will occur at right angle. Yes or no?
Yes.
The other logic is, there are many logic actually. A medium without electric field, but that you will learn later on. A medium without electric field is said to have constant potential. So the entire volume of conductor is an equipotential surface. I mean, of course, I haven't taught you potential, so that's why I was not taking this idea. But you can remember this as of now, as a fact. Entire volume of conductor behave as equipotential volume. So no matter which 2 point you choose, let me do a small part of it. So the potential of this point will be same as this point, will be same as this point. All point will have same potential. So conductor having this very unique property that it will have equal potential for every point, whether you take point on the surface, on the volume, it doesn't matter. So wherever the field is zero, the potential becomes a constant quantity throughout the space where the field is zero. That's very unique property, and you will also understand this very easily when you come across the concept of potential. But imagine you're saying, sir, no, that the field can be at right, I mean at some angle. Then this electric field will have two components. The perpendicular and the tangential. And if there is a component along the tangent, there are two things. Because conductor will have free charge, so the tangential field will move the free charge, yes or no? See,
Yes.
I cannot move along the surface, but I can move, say I cannot move normal to the surface, but I can move the free charge along the surface. Yes or no? And if free charge will move along the surface, can we achieve the electrostatic equilibrium? No, the charge will never be at rest. But it is the property of conductor to achieve the electrostatic equilibrium. And what they do is they eventually create a distribution which nullifies the tangential component, and they are left with only normal component. So the net field is again going to be normal. This is one way of thinking. The other way of thinking is, since it is equipotential, so potential difference you will learn later on is given by the formula E dot dr. If parallel will exist, then if you take 2 points, 1 and 2, dr separation away, you will get potential difference value, correct? So the V2 minus V1 will be non-zero, which means V2 will be not equal to V1.
Yes.
But this is the violation of the assumption, it's equipotential. Understand? Okay, anyway, in the potential chapter, this will be actually clear what is the meaning. But as of now, you can remember only one thing. The near the flat surface, near the closed surface of any conductor, the field is going to be normal to the surface. Is this clear?
Yes.
And therefore, it is mandatory that when you draw the field lines, it must begin or terminate at right angle. Because when you are going to solve the MCQ and if you see there are 4 options given, if the lines of force is terminating on the surface at angle other than 90, it means it is wrong diagram. You can reject such diagram. Okay. So this idea is clear. The net field is 0 idea is clear at least.
Yes, sir.
So this is the main idea, that the resultant electric field inside the volume of conductor must be 0. Okay. So the next topic that I will teach you something is called electrostatic shielding. You can say electrostatic shielding or shielding effect of conductor. So generally, if we have a conductor, now this is the cavity. So a conductor with cavity. So now imagine a situation in which the conductor is, this is conductor, and we have a charge kept inside the cavity. So this charge is inside the cavity, as you can see. What is the first event that will take place? The first event is the lines of force will emerge from the plus charge, correct?
Yes.
But we know that the net electric field in the bulk of conductor must be 0.
Yeah.
Which means the lines of force we cannot draw to be passing through the conductor. Yes or no? So can we draw the lines of force through the conductor?
No.
No. So every lines of force which leaves the plus charge will terminate somewhere. Where it will terminate?
Surface.
The inner surface of cavity. Yes or no?
Yes.
And how it will terminate? At right angle. Yes or no?
Yeah.
The termination must occur at right angle. Guys, please tell me, everyone. I want to listen in unison.
Yes, sir.
How the lines of force will terminate?
Perpendicular.
At right angle. And why? I think the why should be clear, because we cannot draw. Okay, first of all, again, the lines of force is a graphical representation of a resultant electric field. So I cannot draw individual field. I can only draw resultant field. Okay. And from the discussion just before, we can say that since the net field is going to be 0, now how it will happen, don't worry about it. Because the net field is going to be 0, so every lines of force which begins from the charge must terminate on the inner wall of cavity. Yes or no?
Yes, sir.
So let me draw this at right angle. And depending on the placement of the charge and the shape of cavity, the field lines will be something like this. Much creative. So this is the field lines, and a negative charge layer will deposit. Doesn't look actually. So a non-uniform charge distribution will appear. A non-uniform charge distribution will appear on the inner wall of cavity. Is this clear? Tell me, guys, yes or no?
Yes, sir.
Yes, sir.
And if the negative will appear on this inner wall of cavity, then plus will appear somewhere. Where?
Outer wall.
Outer.
Outer wall. So now what is interesting? The confinement of the electric field lines in the cavity is shielding the charge which you have kept inside to interact with the outer world. That's interesting. So I have kept a charge Q inside, and I know this charge and the induced charge on the inner wall of cavity will confine the field lines, and therefore the cumulative effect of the charge which you have kept inside and the induced charge on the inner wall of cavity, their domain is ending there itself. What does it mean? The electric field due to the charge and the induced charge together will vanish up to the boundary. The other induction process, the plus charge will induce outside, and this plus will create its own field. So any charge if you bring to this universe, the interaction of this will be with which field? This will interact with the charge on the outer surface of conductor. Do you realize this?
Yes.
See, the field of the inside charge and the negative induced charge will be ending there only. And the field, the net field which the outer surface will create, that will interact with the world outside. So the first thing that you need to remember, that who interacts with the world outside the conductor? The answer is only the charge on the outer surface. Now, of course, individually everyone is interacting. Now, I cannot say that the Q is not interacting. The idea is this charge is interacting, the induced charge is interacting, and this is interacting. Actually, there are three types of interaction. But the inner two will always cancel each other effect. Why? Because they cannot produce the effect beyond the cavity. So any point beyond the cavity, the two will have null effect. Do you realize this what I'm saying? Any point beyond this region, these two charges will create the zero effect, the induced and the Q charge. Are you getting the idea what I'm saying?
Yes.
Yes.
And only the outer charge will interact with the outer world, and the inner charge will interact with the cavity world, the world of cavity. And there won't be any interaction in the volume of a conductor, where the bulk of conductor is present, which is also called the meat of conductor, the flesh of conductor. Now these words are very non-veg, but in American textbook they use it very often. Anyway, so we can only say bulk. Now you should be aware of this terminology. It is also called meat or flesh of conductor. So the empty space of conductor will have the field due to the plus and minus. The rest will have the bulk will have the zero electric field, net value will be zero. So let me just write down each term independently. So what I'll do is I'll just put some name. So let's say E1 is the electric field. I'm writing the individual capacity of each charge distribution. So let's say E1 is the electric field due to charge kept inside the cavity. Let's say E2 is the electric field due to induced charge on inner wall of cavity. And let's say E3 is electric field due to induced charge on outermost surface of conductor. Okay. Now let's say one fine day someone is asking you what kind of interaction will be with this charge. Now if you want to know the interaction with Q charge, don't try to draw the field of that charge, because I have explained earlier that the force is the localized phenomena of electric field present at that location, except that charge. So if I want to know the interaction of the capital Q charge, then I should not draw the field lines of capital Q, because it is the test charge, it is going to experience it. the other field lines will explode. Okay. So now, if I call the region 1, and if I call this as region 2, and beyond if I call region 3, in a region 1, do we have electric field, yes or no? In a region 1, do we have electric field, guys, yes or no?
Yes.
Yes, sir.
Yeah.
And the field which I have drawn in the cavity is due to which charge?
The charge inside the
Charge
cavity.
Inside the cavity.
No. The electric field in that cavity is the vector sum of 1 and 2. The field is due to the charge inside and the induced charge both, not only one charge. Understood? Because the plus charge is emanating the field lines which is terminating on the negative charge, right? So both are the contributor field, isn't it? In Gauss law, the E represents what?
Net field due to all charges.
Due to all charges. Okay. So in the cavity, the field is due to the plus charge which you have actually put and the induced charge as well. Don't think it is only due to the plus charge. This is a wrong assumption. So first thing first, you have to remember the inside, the field is due to 1 and 2. That's the first thing. In region 2, the E net is how much?
0.
So we know E net is 0,
Yes.
which implies E1 plus E2 is always 0. Understood? So the E3, the word E3, the plus charge on the outer surface will have only field on the outer world, not inside. So when we have a charge over a closed volume, they cannot create field inside. Why? If they move together inside, they will intersect, which is not possible, right?
Yes.
And it is also not like they will go inside and they will decide, oh, no, this is not the right way, let's move away. They will not do like this. Okay. So in the region 2, the 1 and 2 will be always 0, which means the 1 and 2 will be always equal and opposite. These are very, very important concepts. Also, now this is also important. In a region 2, the value of E3 will be how much? So when the charge is on the outer surface, it will create the field outside. And the field inside, the region 3, so the charge on the outer surface cannot have contribution inside the closed volume. So in the region 2, E3 is also 0. In fact, E1 plus E2 and E3, all is 0, sum is 0. But E3 is independently 0 and E1 plus E2 is 0 together, not individual. So if I ask you at this point, what will be the direction of electric field at this point due to induced charge on the inner wall? Can you find the direction of electric field at the point P due to the induced charge on the inner wall? It must be opposite to the field of the plus charge, right? At point P, the E2 Must be like this. Yes, yes or no?
Yes.
Why? Because we know the E1 is like this.
Yeah.
Do you realize this?
Yes.
Because the E1 direction we know already, and because the net is 0, the E2 is bound to be opposite direction. So only with logic you can find the direction, not with actual doing some calculation. You have to just remember the logic. So what you know and what you don't know. Okay. Is this clear, guys?
Yes, sir.
Yes, sir.
And the moment you come outside, the the charge on the outer surface will create its own field. But E1 and E2 will be again equal and opposite. So at this point also, because the scope of E1 and E2 is only in the cavity. So if E1 is there, at this point also E2 will be like this and E1 will be always, no matter which point you choose. So E1, E2 always are equal and opposite pair, so they cancel each other effect in everywhere outside the cavity wall. Okay. And what about the last in E3? In E3 will be equals to E3 only. Actually. Only the outer surface will have the contribution. That's it. Okay. So in region 3, the field is only due to the outer surface. Because anyway, E1 and E2 will cancel out each other effect, right? So whatever interaction will occur with the world outside the conductor is due to the outer surface charge. Is this clear, guys? This is very, very important.
Yes, sir.
Okay. So I'll give you some nice example to draw the diagram and then solve the question also. So imagine we have a spherical conductor. So conductor itself is spherical, which is really good. And if I create a spherical cavity as well, and if I keep a charge somewhere here, question is draw the field lines, draw the resultant field lines. I mean, of course, after the induction, and assume this charge to be Q. You know how to draw the lines, field lines? I will mention here is spherical conductor with spherical cavity. So once you're done with the drawing of the field lines, do let me know. And also tell me the distribution on the inner wall of cavity will be uniform or non-uniform. Am I audible, guys?
Yes, sir.
Yes.
So tell me, guys, that the distribution of charge on the inner wall will be uniform or non-uniform?
Non-uniform.
Non-uniform.
Very good.
On it.
What about the outer surface?
It will be uniform.
Very good. So everyone is able to think why the outer surface is uniform?
Yes.
Very good. Because the inner cavity surface and the charge, they cannot influence the outer world, right?
Yes.
And therefore the outer charge will take its own course and will decide the distribution. And because of the shape of a conductor, it will always repel equally. I mean, they will distribute uniformly over the surface. And therefore the outer surface has nothing to do with the position of inner charge. The distribution of the outer surface is always going to be uniform, whether you move the inner charge from any point to any point, isn't it?
Yes, sir.
So now I think you have drawn the lines of force, right?
Yeah.
So you can see it should be something like this. The nearest point is at right angle, something like this, something like this. Looks nice. Okay. So the field lines inside the cavity will look like this, something non-uniform distribution. But what about the outside? So outside is going to be uniform, right?
Yes.
So what about the magnitude of charge? The charge here will be minus, the net index will be minus q, and here will be plus q, right?
Yes.
Now the outer surface charge is not the charge which you have given, it is the induced charge, right?
Yeah.
And if you draw the field lines, just draw it. And now there is the interesting thing. If I ask you what is the force between this charge q and the sphere, force between q and sphere, and of course they will not do this all induction process. They will only give you, they'll put a charge in the cavity and they'll tell you that okay, if we have a charge which is outside, and one more thing, yeah, just and distance of this charge from this charge is, let's say, s, and distance of the center of sphere to this charge is d. So what will be the force between q and sphere? Anybody? So we have discussed that the q will interact with the outer charge, right? And
Yeah.
the outer charge is as good as a simple uniform sphere. So it's like a point charge. Correct?
Yes.
So can we this is k q by something square? Now what is something here? The separation must be taken from where to where?
From the circumference of the sphere to the
To
cube.
the cube.
Very bad. It is always the center, not circumference. Every spherical charge we consider at center, na? How can you forget this? The entire charge is, if you look at the lines, field lines, these field lines, from where it is coming, if you go back, where it will converge?
The
From
center.
the center.
Center.
So for every spherical distribution, we take center, how you can say its surface? So the distance that will take is the center of the sphere and the charge cube. That's why I just gave the S to confuse you. Understood? I think this is not clear. The force part is clear, yes or no, guys?
Yes, sir.
Yes, sir.
Yes, sir.
So force is due to the outer. So you can think this way. You can replace the entire conductor by a simple a shell with charge q. And from the center of the shell at a distance d, we have charge q. What is the force? We know the answer. AQ by R square.
Yes.
And the R must be the D. The D must be taken from the center of the sphere, not from the actual charge location. Okay. Is this clear, guys?
Yes.
Yes.
So in the electrostatic booklet which I have shared, you can start solving. You can solve a lot of questions. They are very nice question based on cavity. So if I give you a conductor and if I make the cavity large enough, very big cavity, so a very big cavity is as good as thin shell, right? So can we imagine a shell as a solid conductor with almost entire thing is cavity? That's the idea of shell, right?
Yes.
Okay. And if you have any charge here, it will have the similar pattern. Let's say if I put a charge here, it will induce the negative charge on the inner surface. Yes or no?
Yes.
Now, however thin the conductor may be, but there is some thickness. Can we have zero thickness physically possible?
No.
Right. So, however thin a shell may be, you will always have plus and minus induction on the two sides. And this idea is very, very important from the point of view of solving concentric shells. So this Q will induce minus Q on the inner wall and plus Q on the outer surface. And again, let me tell you, no matter how I position the actual charge, the outer distribution is bound to be uniform. And if the inner charge is also symmetrically placed, that is, if it is at the center, we can say that all distribution will be uniform. Yes or no?
Yes.
Now, the idea of shell is when I say this is a shell, mathematically, the two surface will be having some distance. So if it is R, this may be R plus thickness. But calling shell is technically T tending to 0, which makes sure that the two surface having equal radius. Okay. So in physics, when I say a shell, and if I don't mention the thickness, it means I want you to consider the radius of the both shell numerically equal. But there are two layers, there are two shells which you have to understand. So here we have two spherical shell, not one shell. So this diagram is representing two sphere of opposite charge but same radius. Do you realize this?
Yes.
Yes, sir.
So here we have two layers of surface. So every layer of surface creates one charged shell. So metallic shell is one, but how many charged shell we have?
Two.
Two. We have two charged shells. So one metallic shell is equivalent of two charged shell and of equal radius. So the whole purpose of calling this a shell is that you can take both radius same. Otherwise, if they mention thickness, it means you have to take two different separate radius for the given shell. So that is the whole idea of thinking. I hope this is clear to you guys.
Yes, sir.
Yes.
So now what I will teach you next is not very much part of JEE syllabus, but it's good to know. So imagine we have a large metallic sheet. Right? Okay. So this is the metallic sheet, as you can see. So if I have a charge here, and let's say it's an infinite sheet. Okay. It's good. So if it is infinite conducting sheet, and if we have a charge like this, which is kept at a distance h from the sheet, every field line that will emerge from the charge must terminate on the surface, yes or no? Why?
Yes.
Because electric field lines cannot penetrate through the conductor. Because the moment it will enter the conductor, it must be zero, yes or no? So however thin the sheet may be, it will have some physical thickness, yes or no, guys?
Yes.
And in that physical thickness, the field must be zero, yes or no?
Yes.
Yes.
So here it will create a field in terms of concentric rings in which the radius will grow between the ring as you go away. This is just an idea how to grow. If you draw the field lines, now this is very difficult. You can keep on drawing like this, then keep on drawing away, away, away. Simply land anywhere. It will be a diagram like this, like a fountain.
Yes.
So field lines will emerge like this, and like a fountain, it will come back to the ground because the negative charge will be induced here. So the entire sheet will be negatively charged. Correct, guys?
Yes.
And the pattern of the field lines will be like a fountain, but when it will hit the hit the surface, it must be hitting at what angle? 90 degree.
And
So all fountain will hit at right angle. Do you realize this? Yes or no?
yes.
Yes.
And it will be like a 3-dimensional, but if you draw in 2-dimension, it will be pretty easy to draw. You can draw the thickness like this and draw a charge. Something like this, okay? So these are the lines of force that you should know how to draw it. And we have something called method of images to solve question of Erodov, but I think method of images is not part of JEE syllabus. So if you want, you can watch my some other previous videos which I have shared, where I have explained the method of images. It's not part of JEE. So it can be taught, but it will take your time. So you want to learn the method of images?
Yes.
Okay. So now we have seen that the metallic sheet is negatively charged, right?
Yes.
If metallic sheet is negatively charged, and if it is plus charge is actually kept, so can we expect the attraction between these two?
Yes.
So we are assuming the infinite sheet, and this is the charge here, h distance. Now method of images says that you can always replace the conductor by assuming another charge on the other side at the same distance as that of the object, that of the charge, and by reversing the polarity. This. So you can imagine another charge which is presumably on the other side of conductor at the same distance, and the behavior of conductor is as if it is acting as a mirror. So the moment you consider this as a mirror, this will have the reflection here, right? But in the reflection, you must change the polarity. That's the whole idea. Now, what is the force between this charge and this charge? So now you can replace the initial setup by a new setup in which we don't have conductor, we have only charge. And the separation is how much? Which so force will be how much, guys?
KQ square by 4H square.
Now this is the question from IE Rodok, which is pretty easy. Replace the conducting sheet by assuming another charge on the other side at the same distance, because it's like a plane mirror. So every sheet will behave as
Mirror.
mirror. Okay. So if it is plane, so a plane mirror. If it is curved, then we take as curved mirror. Okay.
So this method can be used to solve.
Yeah. I'll give one more question that you will understand what is the importance. Imagine we have two conducting, or you can say, think of one conducting sheet, which is bent in the shape of L shape, like this is the side view. So the sheet is like this, and it is indeed infinite. So this is the sheet, and now we have a charge which is kept somewhere here. So this will also create the induction, right?
Yes.
Now someone may ask you, find the force between this charge and the induced charge on the conductor, or what is the force between, finding force between charge and conductor. So induction will create some negative charge, so there is a chance of attraction, yes or no? Now if you know the ray optics, the method of images, so for mutually perpendicular mirror, you will get 4 images in which one will coincide with the object itself. The image will look like this. So this charge will create the first image here, and this will be a negative image, minus charge. Don't worry, you will learn all this thing in ray optics. And similarly, the mirror below will make the minus charge here. Okay. Or let's make it 45 to make it easy for calculation. Now we have done with the 2 images. The Q will make it minus Q image. This is the minus Q image. But there is one more image on the diagonal. And this image is going to be positive. Why? Because this is the image of image. You can extend the mirror, and of course, this is the idea from the ray optics. You can extend the mirror, and then this will form the image here, and the image of this is also here, so these two will coincide. So you will end up getting only one image. So we have in total 3 distinct images, and the 4th image is coinciding, which you cannot see. And now it is a question of because this is R, so this is R by root 2, and this is R by root 2, right? You can think in terms of distance.
Yes.
So it's a square. So now if you analyze the force, which we have done already, the minus will attract, we can call it F1 and F1. But plus will repel. So the net force will be how much, guys? Can we say 2F1 cos 45
Phosphor.
minus F2?
Yes.
Yes.
And we can substitute the value of F1. F1 will be KQ square by how much? Who will tell me? KQ square by Come on, guys. Tell me.
2r square.
2r square. Very good. And F2 is how much? AQ square by?
It's also 2r whole square. So that would be 4r square.
4r square.
So that is a 4r square, and definitely our answer is eventually KQ square by r square into 1 by root 2 minus 1 by 4. So this is the net force. So for any geometrical shape, you can do this method of images. For plane mirror, if you know the chapter of mirror, then only you can solve. If you don't know, you can't solve. Okay. So don't worry. This is the idea. Keep the idea intact in your brain, and the moment you study the geometrical objects, you can come back and realize what is happening. Okay. Just a moment. Okay, so I think I should leave the today's discussion here. But okay, before I leave, I'll just finish the part which is called the electric field due to infinite conducting sheet. The last topic, E due to infinite conducting sheet. So if we have a conducting sheet, so the sheet may be thin enough, but can we have zero thickness possible?
No.
You may do as thin as possible, but you cannot have zero thickness physically. So now something very interesting will happen. The charge given to a thin metallic sheet, if you give some charge, it will spread over the surface, and that spread will be independent of thickness of the sheet, isn't it? So we have seen here the charge which I have shown here. This charge is actually on the surface, and this charge is not out of the surface. It is actually in the bulk only, and it occupies some thickness which we don't generally represent. You know what is the thickness in which the charge will spread? Can you guess? This thickness is up to few nanometer. That's it. So there is nothing like charge outside the surface. It is still in the volume of conductor, because that is where the charge will reside. Charge cannot, will be on the flying. They are not like drones, flying over the conductor. They are very much inside the conductor. And the idea of what is the idea of surface? I might have discussed many times in past. What is the concept of surface, guys? Whether it is liquid or solid. Okay, we don't define surface for gas. So whether it is liquid or solid,
It's
what
a
is the
layer
surface?
of some nano.
The first 5 to 10 atomic layer of the medium is called surface.
Yes.
And therefore, you can say the minimum thickness, like the idea of surface is the thickness of surface is roughly equals to 10 angstrom, because one atomic layer is 1 angstrom. I hope you know the dimension of atom is in angstrom, and this is roughly I'm saying 1 nanometer. I mean, this is rough. This is exact. This is rough. So the roughly the thickness of over which the charge will reside is up to few nanometer, which you can say up to few angstrom. And any physical thickness, it can be as thin as micrometer. Let's say you can use a hammer and you can make the, if you go to some sweet shop, they use the metallic thin foil which they put over the sweets. You might have seen during Diwali, you will see very often. Also, you can see normally they use the aluminum foil most of the times in the name of silver foil. And if it is really expensive, they use the gold foil. Now, the gold is having the best thing about gold is it is the most malleable metal, right? I hope you know.
Yes.
And it is so malleable that you can create a thickness as thin as a fraction of millimeter. It's such a thin layer you can create from the gold, and that is the reason why the Rutherford used the gold foil in alpha scattering experiment, because only with gold we can create the thinnest possible layer. And that's why you can see that even a gold jewelry in 5 grams they can create as big as, let's say, 1 square foot area they can cover with 1 gram. I said less, it is much more than that. With 1 gram of gold you can cover maybe how much, 1 BHK, maybe you can cover 1 BHK, I don't know. It is so much malleable, and that's also the reason why we use gold in manufacturing the jewelry. It's of course the brightness, the shining, the luster, and the malleability is the main reason. You can actually design as you wish. So now the thickness is micrometer. So if you compare the micro with a nano, I hope you know. So in 1 micrometer, how many nanometer we can have? 10 power 3, right? I hope this is clear.
Wow.
10 power 3, no? Yes. Okay. So even though you will think this is the thickness of the metallic sheet, the charge will occupy a layer only up to few atomic layer. Again, these are only for illustration. So no matter how thin you believe the charge is, the surface is, but there is some thickness. And I have simply zoomed the thickness to demonstrate all this. And now our thickness of charge is here. This is the thickness of charge actually. So now there is something called thickness of the conductor, that's called DEET actually. And I'll keep the original convention, the thickness of charge layer so every given charge Q, the half will appear on this side and the other half will appear on this side. Do you realize this? Up to some thickness, which is so T is roughly 1 nanometer. Okay. And why I'm explaining this, because sigma is something really interesting. In this case, the sigma we define for each layer, not for the entire surface, not for conductor. So the sigma we can define as rho into T. Now T is the not the thickness of the conductor. T is the thickness of the layer of charge. That's very interesting. Here T T actually represents the thickness of charge layer over the surface, which is much lesser than the thickness of the metal itself. So however thin a foil you may create, it will have a surface, a bulk, a surface. I mean, surface and bulk. So no matter how thin it is, it will still have the surface and bulk. Do you guys realize this part? That every conductor will have surface and bulk?
Yeah.
And no matter whatever charge you give, the charge will only reside on the surface, not in the bulk. So any extraneous charge given to conductor only appear on its surface. That's a very, very crucial result that you must remember. Let me write it here. I think someone is getting late for the next lecture. Raise your hand. If someone is getting late for the next lecture because you may have lecture at 9 o'clock. In that case, raise your hand. I can continue for some more time. Okay. Okay. Then I think. Okay, I'll stop here only because I think it will take some time. But let me just mention the last word. Oh, okay, fine. Come in the next lecture, we'll discuss. So now you can solve almost all questions of SC Verma except the last few questions in which we have the parallel connectors, which I will take care in the Capsida chapter. Okay. So in SC Verma, you have Gauss law. Please go and solve.
Yes.
Those who are getting late, please leave. I'm also leaving. Anyway. So good night, guys. Take care and start solving the Gauss law and try to finish as much as possible. Also from the 41 years or 42 years or 44 years of old JEE.
Do you have the PDF of that?
I have old one. I have up to 2018 something.
Okay.
I can share that one. Anyway,
Yes.
that is good enough. The latest one I don't have. All right. Bye, guys. Take care.
Bye, sir. Thank you.
Thank you, sir.